Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today we are taking a deep dive into a very crucial topic from Unit 3, current electricity. We'll be talking about cells in series and in parallel. We promise to make this concept simple, completely exam safe, and something you will remember for life. So let's start with a simple question. Tell me, why does a small toy car run perfectly fine on just one 1.5 volt AA cell? But a standard flashlight, a bright one, often needs two 1.5 volt cells connected together. If one cell has enough charge, why do we need two?
Yes, that's right. I've always thought that more cells just meant more power, but I'm never quite sure what we're gaining. Is it more voltage or is it something else?
Exactly, and this is where it gets really interesting. If you look at an electric vehicle, like a car, their batteries use hundreds of small cells. They arrange them in these massive packs. But they don't just put them all in series for a huge voltage, nor do they put them all in parallel for a huge current capacity. It's a combination of both. So we need to understand this fundamental trade-off. Is connecting them for a higher push, that is higher voltage, better? Or is it better to connect them for higher endurance, a higher current capacity? And the difference depends entirely on how we handle the cell's own internal resistance.
Internal resistance. That's the part that's always a bit confusing.
Okay, let's unpack this. The core idea is simple. A cell provides two main things. First is its EMF, which is the internal chemical driving force. And second is its internal resistance, small r, which limits that force.
Okay, EMF and internal resistance.
Right. Think of a cell like an escalator, raising the charge carriers, let's call them people, to a higher electrical level. The total height of this escalator is the EMF.
So the EMF is the total potential lift it can give.
Precisely. But the friction inside the escalator's mechanism, the gears and motor, that is the internal resistance. It causes some energy loss. Now, let's visualize how we can combine these escalators. First, a series combination. Picture placing two escalators, one after the other, end to end. A charge carrier rides the first one, gets a 1.5 volt lift, and then immediately steps onto the second one and gets another 1.5 volt lift. So what is the total potential rise?
The total rise would be 3 volts. The voltage just adds up, right?
Correct. Now think about a parallel combination. Picture two escalators standing side by side. Both start at the same level and end at the same level. The total height, which is the voltage, remains 1.5 volts, but now...
Now twice as many people can pass through at the same time. The charge flow can be double.
Exactly. So that makes sense. EMF adds in series. But what happens to the internal resistance? That friction must change, no?
That's the main doubt. Does the friction also add up in series?
That is the critical question for your exam. The change in internal resistance is what determines the final current capacity. Now let us see how NCERT defines this, starting with the formulas for a series connection.
Okay. For N cells connected in series, the formal definitions are: total EMF is the sum of individual EMFs, which is epsilon total equals epsilon 1 plus epsilon 2, and so on. And the total internal resistance is the sum of individual internal resistances. So R total is R1 plus R2, and so on up to Rn.
You see, everything simply adds up in series. It's quite straightforward. Why? Because the current is the same for both cells. Charge conservation requires the same current to flow through cell 1 and then cell 2 sequentially. So the resistances just add up.
Okay, that part is clear.
Now for the parallel case, could you please read the formula for internal resistance in parallel?
For N cells in parallel, the total EMF remains the same. So epsilon total is just epsilon, assuming they are matched. And the total internal resistance decreases by the reciprocal rule. 1 by R total is equal to 1 by R plus 1 by R2, and so on.
What's fascinating here is that adding more cells actually decreases the resistance.
Oh, right. It's like resistors in parallel.
Yes. This is like opening multiple lanes on a highway. The equivalent internal resistance becomes very small, and that is the secret to getting high current capacity without an excessive voltage drop inside the battery itself.
That makes sense.
But there is a very crucial condition for parallel combination. All the cells must have similar EMFs. Do you recall why this is so important? Otherwise, we risk damaging them.
Yes, I remember reading this. If the EMFs are different, the higher EMF cell will start forcing current backward through the lower EMF cell, isn't it?
Exactly. It will try to charge the weaker cell.
And that would damage the weaker one.
It would. It wastes energy and can permanently damage the battery. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now let's look at a very simple worked example to seal the deal. Suppose we have two identical cells, each is 1.5 volts and has a 0.5 ohm internal resistance. We connect them to an external 5 ohm resistor.
Okay, two cells, one resistor.
First, let's do in series. The total epsilon is 3.0 volts, and the total internal R is 1.0 ohm.
Right, 1.5 plus 1.5 and 0.5 plus 0.5.
So the current I is the total voltage divided by the total resistance. That's 3.0 duovolts divided by what's the total resistance?
It would be 5 ohms from the resistor plus the 1.0 ohm internal, so 6 ohms total.
Perfect. So the current is 3 divided by 6, which is 0.5 amperes.
Okay, 0.5 amps.
And the terminal voltage, which is the voltage across the external resistor, is I times R. So 0.5 amps times 5 ohms gives
2.5 volts.
Exactly. And the power delivered is 2.5 volts times 0.5 amps, which is 1.25 watts. Keep that number in mind.
1.25 watts.
Got it. Now let's look at the parallel case. The total epsilon is only 1.5 volts, but the total internal R is now much lower.
It would be the reciprocal rule. So 1 over 0.5 plus 1 over 0.5 gives a total of 0.25 ohms.
Correct. A much lower internal resistance. So the current is 1.5 volts divided by the total resistance, which is 5 plus 0.25, so 5.25 ohms.
Okay, so 1.5 divided by 5.25, that's about 0.286 amps.
Yes, approximately. And the power delivered, it's much lower, around 0.408 watts.
Wow, that's a big difference. 1.25 watts versus 0.4 watts.
What does this tell us? For this 5 ohm load, the series connection gave a much higher voltage and much higher instantaneous power. So series is better for applications that need a higher voltage to operate. Parallel is more about extending the runtime and minimizing voltage drop when you need to draw a very high current.
So understanding how epsilon total and R total change it's the most important part.
Absolutely. Because these totals, these equivalent values, they become the starting point when we move on to analyze complex networks, which we do using Kirchhoff's rules in our next concept. Okay, now let us discuss 2 common pitfalls. These are the silent killers that cause students to lose easy marks in exams.
Okay, what should we watch out for?
First, silent killer. Many students wrongly assume that connecting batteries in parallel always increases the power delivered.
Why do they think that? I suppose just because more cells means more power in their mind.
Yes, but they ignore the voltage factor. Parallel keeps the voltage low. And since power is V squared over R, for a fixed load, a lower voltage often means lower power. Just like in our example, right?
Right, 1.25 watts versus 0.408 watts. So parallel is mainly for current capacity and runtime, not for increasing instantaneous power.
Perfect. Now for the second silent killer. Students believe that adding cells in series always increases the power delivered to the load.
Ah, this one seems more intuitive. If you increase the voltage, shouldn't the power also increase?
It seems like it should. But while the EMF does increase, the total internal resistance, R total, also increases. It adds up with every cell. So if your external resistance R is very, very small, say much smaller than the internal resistance, then most of that extra voltage is just lost as heat inside the batteries themselves.
Oh, I see. So series increases the push, but it also increases the internal friction. That friction can choke the current if the external load isn't big enough to matter.
You've got it. The net effect depends entirely on the ratio of the external R to the total internal R. To lock this concept in your memory, here are some anchors. First, the crucial phrase. Series for voltage, parallel for current capacity. Say it again.
Series for voltage, parallel for current capacity.
Good. For a visual gesture, imagine the series connection. You hold hands with another person and climb stairs together. Your combined height, that's the voltage, it's the sum of both heights, and you both climb at the same rate, which is the same current.
Okay, holding hands and climbing.
And for parallel, you stand side by side at the bottom of a ramp. Both of you can walk up, same height gain, so same voltage, but now the two of you can carry twice as much luggage. That's twice the current capacity.
That's a great visual.
And finally, a simple mnemonic series. Add voltage, add resistance, and parallel, same voltage, add conductance. Conductance is just the inverse of resistance, so it's an easy way to remember that the total resistance goes down. And just think of a real-world example. A car battery is 6 2-volt cells in series to get 12 volts total. That's a classic case of series for high voltage.
And the EV batteries use parallel to get the high current.
Yes, hundreds of cells in parallel strings to achieve that massive current capacity, all in one pack. So, here's your 3-point summary for exam preparation. First, in a series connection, EMFs add up and internal resistances also add up. This configuration is used when a higher working voltage is needed. Second, in a parallel connection, the EMF remains the same, but the internal resistances combine using the reciprocal rule. This leads to a much lower total internal resistance, which is done to increase current capacity and battery runtime. And third, combining cells in parallel requires all the cells to have matched EMFs. This is to prevent the internal discharge of a weaker cell by a stronger one, which would waste energy and damage the battery. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROF, Sam, right?
Yes, PROFSAN.com. Thank you for joining us for this deep dive into current electricity. Study hard and keep learning.